So this morning when I was commuting, I was reflecting on how I ended up here today, right? And as Jerome said, we met for the first time a couple or 3 years ago, more or less. I was working in ADP as machine learning engineer, and we had some people from Inno in there. And I think the relationship has been like strengthened these years, and we have more people than then. So I'm happy to see that our first conversations make this fruit. All right, so what I'm going to talk today is about how can we transform scientific literature into discovery, knowledge, new hypotheses using AI. It's a kind of, when Jerome invited me to this talk, I thought, okay, how can I present this work? So it will be a little bit of high-level stuff and also some more deep-level technical scientific part. Okay? So it's a mix of both, and I hope you enjoy this combination. Now, what's Sony AI? Sony AI is what we call the frontier new AI research lab within Sony Research. It was created in 2020, and as you can see here, there have different flagship projects of this AI. Some of them are more or less related to Sony. For instance, music, we have imaging, cinema, gaming, of course. But there are some others which you might think they are not as much related as Sony as I could think. And one of these projects is scientific discovery. So I'm part of this team. The team is called Haken, and Haken in Japanese, because as you know, Sony is a Japanese company, Haken in Japanese means discovery. Okay? So we've been working for the last 3-4 years trying to improve or develop new models based on AI, which, based on the literature that we have, we can extract knowledge from that, and then we can generate new hypotheses. Okay? That's the main goal. What are the objectives? The what, how, and or what, or why, what, and how. So to advance in scientific discovery, support scientists in generation or discovery of new hypotheses, and all this using advanced AI. So let's do a brief recap of what's human knowledge. So I can think of, or if I think of human knowledge, my image in my head is a big library, probably not infinite library, but very huge library, full of knowledge in the form of documents, books, I don't know, histories, whatever you might think of. And in this very big library, we have basically 3 different sets of knowledge. The first one is what it's called lost knowledge. So it's something that we don't know that we don't know, because maybe it's lost somewhere, we haven't found it, or it's written in a language that we cannot decipher, and therefore we don't know what's in there. The second group is kind of we call private knowledge. So we know that there is this knowledge, but we don't know. Think of it as we know that Coca-Cola has a formula for it, okay? Or we know that, I know, OpenAI trains ChatGPT with given architecture or some data, but we don't know this architecture or this data. So this is something that we know that it's there, but we don't know. And then the final group is the public knowledge. So journals, different books that we have out there, everything that we can, for free or paying, get access to. And this is the most interesting, because we don't know that we know this information. Right? It's a lot of information out there that we don't know that exists. And this is the interesting group for us. So the question now is, how can we leverage this knowledge? How can we make this actionable and make this useful for something, right? For advancing scientific discoveries, for discovering some cures, whatever. So that's the question. And here is when the literature-based discovery comes in. So we get back to 1986, this guy, Donald Swanson, presented this ABC paradigm. This was the first example of literature-based discovery. How does it work? So you have a first set of documents, of literature, which relates concepts A and B. And then you have a disjoint set of documents which relates concept B and C. Now the question is, can we relate A and C? It's a transient relationship. Okay? This was useful because it helped researchers to discover new insights that we couldn't discover before, right? So we have some relation here, some another relation here. Hey, can we mix these two and then make a new discovery? It was also gaining information, but the most important thing, it increased the interdisciplinary information sharing. So think of that date, it was like of a silos, some journals about medicine, some journals about whatever, chemistry. But then this concept made possible to merge these two different worlds or to connect these different worlds, right? Okay, what's the problem? Think that this first approach here was manual one. So it took weeks, if not months, for a person to read different or collect different documents, identify what was A and B in this set of documents, what was B and C in this other set, and then make the connection. So nowadays, we have a huge number of publications every year, new publications. So these are So these are very recent news. And say, for instance, the first one says 3 million papers a year. If you look at the evolution of the number of papers published from 1980 up to today, you see how this curve is. Right? So the question is, how come we can come up or we can deal with such a big number of knowledge? Imagine a scientist sitting in his or her desk reading papers all day. Okay? It's impossible. So we have to resort to some automatic or machine-based methods to build all this. So this is where the evolution of LBD comes in. So at first stages, 1980s, we have this Swanson ABC paradigm. And then from 1919 onwards, we have been increasingly seeing new methods, new algorithms, computational power has increased. So we go from the lexical statistics at the beginning, think of it as back of words, TF-IDF. In the 2000s or so, it's approximate map, this one, ontologies and knowledge graphs came in. Then we discover the embeddings, the world of embeddings. Machine learning made the news in 2010s or so. Then node-to-back or neural networks came in very recently. And today we have LLM and agents. Okay. Where are we as a team? So nowadays we are here, more or less 2026. And our team is here proposing a new approach to LBD. Now, what do we do at Hacken? As I told you, Hacken is the name of our team. Hacken means discovery in Japanese. And as you can see here, we have basically 3 different waves we can group in literature-based hypothesis generation. First one is, wave 1 is based on words. Here we have ABC paradigm, we have TF-IDF, we have statistical analysis like Z-score or co-occurrence, this kind of stuff. Second wave, it's more on the concept level, it's semantic, and here we incorporate knowledge graphs, for instance. And then we can analyze these knowledge graphs by means of graph-based algorithms like community detection, shortest path, this kind of algorithms. And then the third wave, this is what we are today, is based on vector embeddings. And here we have temporal neural networks. Okay? We have embeddings, of course, knowledge graphs as well. But here the point is that we are analyzing the trend of the connections of the graph. So here we have a static one. Here we have an evolution, snapshots of the knowledge. Right? In the first wave, we have like very manual work, although in the latest stages, there were some computational techniques. This one here, we can like analyze hundreds or thousands or millions of documents, but the information is kind of static, and we can predict whether or not a link should be between 2 entities. And here we go one step further and say, we are using time to analyze how the relationships evolve over time, and we are predicting not only whether or not an edge should be in there, but also what type of edge. Okay? We are here. So think of it as, I will go a little bit into the details later, but for now, big picture is we have some knowledge which evolves over time. Okay? And at each point in time, we can build a knowledge graph, which is a set of entities and relationships, out of this literature here, or this knowledge. Then, over time, we can build different snapshots or different knowledge graphs. Okay? And at the end, we say, okay, now what would be this knowledge graph at time t+1? And then we predict what the new edges would be in this graph based on previous knowledge. Okay? So in essence, what we want is discover new hypotheses, but not only this, but also contextualize this hypothesis. So I came up with a new hypothesis, but then the question is, okay, but how did you connect this new or these entities to generate this hypothesis? As a scientist, I want to see what is the relationship between these 2 entities, the hidden one, as we will see later. Okay? So here, for instance, we have come up with this prediction, and then we say, this entity here has this protein, spike 1. Spike binds to this, I don't know what is this, chemical, probably. Then SARS relates to another one. You'll find a path connecting these 2 that supports this new hypothesis. Okay? From this work in the team, in the last 3 years, we have generated some different publications. This one is more about how we generate hypotheses, and this other one is how to explain this hypothesis. So it's a very important, not only to generate a hypothesis, but to be able to explain. As you know, these LLMs or these large language models are kind of black boxes that you don't know what's in there. So we try to explain not only, so that what or why did we come up with this hypothesis. Now, going a little bit deeper into the model. So if we frame this hypothesis generation problem as a temporal graph, I don't know how familiar you are with graphs. Are you familiar with graphs, or yeah, no, more or less, no? Okay, what's graph? Graph is an entity or a tool or a mechanism to explain some concepts and relations between these concepts. So we have nodes, which are like concepts or entities, and then relations between these nodes. Think of it, for instance, a social network. An entity would be a person, and then a relationship is friend of. So person A is friend of person B, for instance. Think of it as molecular networks. Here we have atoms as nodes, and then bonds as edges, for instance. There are many, many different concepts or fields that can be defined as graphs. For instance, I know citation networks. This paper cites this other paper. They are connected. And then you can build a network of citation. This actor appeared in this movie, this actor too. So these two actors appear in the same movie. You can build a network out of it. Okay? So we define the set of nodes as B and the set of edges as E. This is how it's typically defined. So a graph in a given point in time that I shown before, it's composed by a set of nodes, a set of edges, and what we call a set of facts. A set of facts is nothing than a triple. Node A is connected to node B through this edge. Okay? Node A connected to node B through this edge. So we have a collection of triples that describe your knowledge. And then you can build a graph out of this collection of triples. So at the end, what I showed before, so we have a temporal evolution of our knowledge represented as a graph. And our predictive model, it's nothing that, okay, given a graph, what is the probability that node I, J are connected? And based on different parameters, this is what we have to optimize. And basically, what this PAJ is a kind of a vector of probabilities of, okay, if I evaluate this hypothesis here, the probability of these two nodes connected by the first type of edge, let's say treats, is 0.98. The probability of these two edges being connected to by means of this second type of edge is 0.10, and so on and so forth. So it's a vector saying these two, this is the probability that these two nodes are connected by different types of edges. Okay? If you remember, in the second wave of the literature-based discovery, we had only whether or not the edges would be connected. So instead of having a vector, we would have only one number, telling the probability of these two nodes being connected or not. Now we have a vector telling what's the probability of being connected with this type of edge. Make sense? Cool. One big problem, and also an advantage, is time. We can use time to better model how relationships evolve, but we need to be careful about time because we can forget things that happen quite far in the past, right? So this is one of the issues that recurrent neural networks have. So they can model near interactions, but they can tend to forget about very long away or past interactions. So in our approach, what we did was to come up with a hierarchical model which pairs interactions, and it's building upon these interactions over time. So in the end, you have a very big tree, if you want, that contains the information of all time. Okay? Because we are building based on one time dimension, then next step level, we join these two time steps, okay? And in this other one, we are joining 4 time steps, and so on and so forth. So at the end, what you have is an embedding which represents information of all the time. Okay? This is one of the advantages. Another big problem what we have in this setup is that we don't have negative samples. So the literature shows what's been discovered, but it doesn't show what it failed, and therefore we shouldn't look into it. So it's very difficult to come up with negative samples. The way that in the team we addressed this was to, use active learning and curriculum learning. So one way is, okay, let's randomly select negative samples, which is one strategy. In this case, with active learning, we're choosing these negative samples in a more smarter way, let's say. So they are more informative to us. And in the same way, curriculum learning means that we train on positive samples, more complex every time. So we start with very simple relationships, and then over time, we are adding more and more and more complex positive examples. So this is kind of a strategy or strategies for training to overcome these kind of limitations that we have in the data itself. Right? And as I mentioned, we have this temporal hierarchical transformer. This is an overview of the transformer architecture that we have. Now, as I told you, we have 2 different things or important things. One thing is how we predict this hypothesis, and the second thing is how do we explain this hypothesis. And it turns out that if you see how frequently do you use generative AI or AI in the following tasks, and in hypothesis generation, 93% of people don't use AI. Okay? And the reason why, because they are not, or the methods that they use, they are not reliable enough. Okay? So as a highlight, so we can say that scientists won't use or won't trust what they can see or touch. Right? So we need AI systems that are capable of showing or to let the scientists interpret why we come up with this hypothesis or the solution. So this is a picture, say, this is the prediction that we made. So SARS-CoV-2 enters cell via this receptor. And this is the explanation that we give the scientists to support this hypothesis here. Okay. Also, we can have different explanations. This is a very small graph, but for the same hypothesis, as I will show you later, we can have lots of explanations or different explanations. Now the question is, and I will be very brief on that, How can we build these explanations? There are different methods, what it's called rule-based, instance-based, and analogy-based. I won't go much into the detail, and we are using this one here. Okay. So basically what we are doing is, okay, we have a hypothesis, two entities, we predict one relationship. Let's look at the neighborhood of these nodes to see how we can go from one to another. All right? And once you have that, then you have different kind of explanations. One is, what's the necessary explanation? What's the minimum, what's the required for this prediction to happen? It's the minimum one. The second is, okay, what is sufficient? Of course, the sufficient must be necessary, of course, but you can add some extra relationships that don't add any value here, so they are superfluous. What's necessary? And the third one, it's a lot of, well, it's interesting because here we are not linking these two entities by means of an existing path, but we are saying, hey, if we add a new edge here, okay, how likely is that these two will be then linked? Okay. So in this latent explanation is what facts are missing in the graph. Facts, remember, that are triples. So what facts are missing that if we add these facts in the graph, then this prediction is more likely to happen. Okay, so this is the scientific part, high level, but scientific part. The question now is, okay, how can we make this, or how can we implement all this stuff in a real product or a prototype? One thing we have done in these 3-4 years is going from pure research. So as you can see that these papers and all this stuff, it's quite like intense in terms of scientific, weight. But then the question is, okay, how can we actually leverage all this knowledge that or these models that we can build to build a product or a prototype? And we have built this architecture, and later I will do a demo, a live demo. Let's cross our fingers. But basically, high-level stuff is we have used this FTI architecture. FTI means feature, training, and inference. So sometimes, especially when you are developing prototypes, you have your laptop, I would say your notebook, where you have everything in there. Okay? So you have your data, you have your scripts to prepare your data, and then you train your model, and then you do the inference offline or online. But when you want to scale this or to make a product out of it, the best approach is to separate these three steps, separation of concerns. And the glue here is the data itself. So we have some input data, some data sources, and then we run our feature pipeline, and then we generate some new data, which are the features for the model. Then, with this data, we can train the model and save this trained model, and then at inference time, we can load this model and then do the predictions. Why are these three steps separated? Because one reason is these steps, each of these steps can have a different time frame. I might be ingesting data every hour, every day, or every minute. But maybe I'm not training a model every minute. Maybe I can train a model every month or every week. Okay? So an inference can happen in real time or in batches or whatever. So we can actually implement these three things together if we want this feature. So then I'm ingesting some data, I'm generating some features at some point because my model has drift. I can train a new model, and then the inference pipeline will load this model asynchronously, and then we'll make the new predictions. Data ingestion, it's kind of a rather standard ETL. So we have some data sources, data ingestion pipeline, which leaves some raw data in our packets in AWS in this case. Then we do some data transformation, some data cleaning, you know. And finally, we have this processed data that we can load into different databases. In our case, we have Postgres, for instance, and Neo4j for this knowledge graph representation. Then it comes model training. Once we have these features computed, which are stored in our databases, we can extract some features, train a model, and then we log this model alongside the metrics or the hyperparameters, some labels, some whatever metadata you want to log. And then you have a model trained and logged in MLflow in this case. And then at inference time, what we have built is a set of microservices. And each of these microservices, or some of them, rely on different databases and also on MLflow. So one of these services, for instance, the KGE, is the one that doing the predictions. It's pulling the latest model from MLflow, train model, and then make some predictions. If we update the model, the API pulls the new model and do the same, right? If we update the databases with new data, this is available to different services. Okay, what I will show now is a demo of the web app, right? Hopefully this works. It worked half an hour ago. No, not half an hour, but 1 hour ago. So to give you a bit of a sense of what we have built. So this is our user interface. And this is in the development environment. So basically what we have here is, okay, we have this is our hypothesis that we want to generate, and we have these different elements. So the subject, relation, and object. And then we can choose, for instance, as a subject, I want, I don't know, a chemical that inhibits, I don't know what I'm like asking for, to be honest. I mean, for this. And then we can add this hypothesis to our queue, and you can see in this diagram here, this is our hypothesis. So what I'm doing is, I'm, in this case, fixing or the type of relationship, okay, this element here, and say, hey, give me some perspective or do some predictions about what are the chemicals that could like follow this hypothesis. And then I can run. I take some time sometimes. Now our system is querying this architecture that I shown to you, this KGE model, and then here we have the predictions. So what do we have in here? So here is the hypothesis that we are testing, and these are the candidates for this element X. Okay? For each candidate, we have a kind of confidence score, and then we have also what is the literature or the documents or the papers that support this hypothesis. So here there are like papers in which this chemical appears and also this element here appears. So you can say, hey, I extracted this hypothesis using these documents. Okay? Not only this, but we can say, or we can ask, okay, but give me the actual paths that you queried in the knowledge graph to support this hypothesis. And then we can say, we can go here and say, these are the different paths that I found which supports this hypothesis with this element here. Okay? As you can see, we have a connection between this element and this other element by means of different other elements in the middle and types of connections. So this is the kind of explainability that we can provide to the scientists and say, hey, I'm telling you this because there is this connection in the graph. Okay? If we go over, we can see like for each of these connections also what kind of path or the way that we arrive to this. We can do the same for the other candidates, but this is basically the same thing. Right? Let's see these paths here. You can also increase the number of paths that you want to see, and also the complexity. This is also complexity 3, but we can build or search for longer paths or connections. Okay? So this is basically the outcome of these 3 years of research, developing new models, and everything that I've told you. All right, so let's back to the presentation. So basically, this is everything that I had to tell you, but one or two aspects that we are now working on is how good are our predictions? Because that's a fair question, right? So one thing, because this is a very difficult topic here, and we are like sending some of our predictions to a wet lab to actually verify whether these predictions are true or not. This is one point. And also we are exploring how can we integrate this tool into other tools. Think of it of AI agents, LLMs, wherever, to further increase the quality of the results. So think of it as I ask for something in an LLM, and instead of this going only to an LLM, it goes to an agent. An agent says, hey, I'm asking for this hypothesis. I query Hagen, which gives me some candidates. Also have my RAG in here, and then I combine everything to give you a better answer. Well, this is basically like a summary of what we did. First is the speed of how can we leverage all the literature that's out there. Second thing is that hopefully this will be used to inspire or to discover new things and go or unleash new research directions. And finally, as researchers has shown, they are very interested in know the explanations of what these hypotheses come from. A little bit of our references or articles that we have published during these years, and that's it from my side. I hope this was useful and clear, and you enjoyed the talk. Thank you very much.